Have you ever wondered why time seems to fly when you're having fun, but drags when you're bored? An intriguing question, isn't it? You see, our perception of time can be quite relative. It's like when you're engrossed in a good book, time just seems to slip away, and that's a tiny glimpse into the world of relativity. Well, this subjective experience of time isn't exactly what Einstein's theory of relativity is about, but it does hint at the fascinating concept that time isn't as constant as we might think. Albert Einstein, a physicist from the early 20th century, proposed a groundbreaking idea that challenged our understanding of the universe. Born in Germany, Einstein was a curious child who grew into a rebellious student, often questioning established theories. His rebellious nature led him to Switzerland, where he pursued a degree in physics at the Swiss Federal Polytechnic. It was here that Einstein began to question Newton's laws of motion, which had been accepted for over 200 years. He couldn't shake off the idea that something was missing. This relentless curiosity led him to develop the special theory of relativity in 1905. But Einstein wasn't done yet. He expanded his theory to include gravity, resulting in the general theory of relativity, published a decade later. This theory, complex yet elegant, turned the world of physics on its head. Einstein's theory of relativity forever altered the way we perceive space and time. The theory of relativity is made up of two parts. The first part is the special theory of relativity. Diving into the special theory of relativity, we enter a world where the conventional understanding of time and space is thrown out the window. In this world, time can slow down or speed up, and space is not a fixed entity. This might sound like the plot of a science fiction movie, but it's actually the cornerstone of our understanding of the universe. At the heart of the special theory of relativity lies the concept of space-time. Imagine this as a four-dimensional fabric that is woven together by 3 dimensions of space and 1 dimension of time. The objects in the universe, including us, are moving along this fabric. But here's the twist. The fabric isn't flat. It can bend and stretch depending on the mass and energy of the objects within it. Now let's talk about a cosmic speed limit, the speed of light. According to the special theory of relativity, light always travels at a constant speed of approximately 186,000 miles per second, no matter who is observing it. Whether you're standing still, rushing towards it, or sprinting in the opposite direction, the speed of light remains the same. This might seem counterintuitive, especially if you're used to the way speeds add up in our everyday lives. But in the realm of special relativity, the usual rules don't apply. So what does all this mean? Well, it means that our perception of time and space is not absolute. It can vary depending on our state of motion. This leads to some truly mind-bending implications. For instance, if you were to travel near the speed of light, time would appear to slow down for you compared to someone who is stationary. In essence, the special theory of relativity tells us that the laws of physics are the same for all observers, and that light has a constant speed, regardless of the motion of the observer. This is the fascinating world of special relativity, a world where time, space, and speed come together in ways that challenge our everyday perceptions. The second part of Einstein's theory is the general theory of relativity. This is where things get even more mind-boggling. The general theory of relativity is all about gravity, but not gravity as we usually think of it. Imagine you're standing on the ground and you drop an apple. It falls, right? We say that's because of gravity. But according to general relativity, that's not the whole story. Instead, Einstein proposed that gravity is a result of the curvature of space-time. Now, what is space-time? Think of it as a 4-dimensional fabric that makes up our universe. It comprises 3 dimensions of space and 1 dimension of time. This fabric isn't flat. It bends and curves around any object that has mass. So the Earth, for example, causes a dent in space-time, like a heavy ball sitting on a trampoline. And what about our falling apple? It's not being pulled down by some mysterious force. Instead, it's following the curve created by the Earth in space-time, like a marble rolling along a curved path on our trampoline. But here's where it gets even more fascinating. It's not just mass that can curve space-time. Energy can too. This is encapsulated in Einstein's famous equation E equals mc squared, where E is energy, m is mass, and c is the speed of light. This equation tells us that mass and energy are interchangeable, so anything that has energy also has an equivalent mass, and vice versa. Therefore, anything with energy, like light, can also curve space-time. This has some pretty wild implications. For instance, it means that light can be bent by gravity. This was confirmed by an experiment during a solar eclipse in 1919, where stars appeared to shift position because the light they emitted was bent by the sun's gravity. This observation provided one of the first empirical confirmations of general relativity. So, to sum up, the general theory of relativity describes gravity not as a force, but as a bending of space-time. It tells us that mass and energy can curve this four-dimensional fabric of our universe, causing what we perceive as gravity. In essence, the general theory of relativity describes how gravity is not a force acting between bodies, but rather a curvature of space-time caused by mass and energy. So why does the theory of relativity matter? How does it impact our daily lives? Let's start with the technology we all use every day, GPS. This global positioning system is a network of around 24 satellites orbiting Earth, sending signals to our devices. But the satellites are moving at high speeds and are far from the Earth's surface, which means both special and general relativity come into play. Without accounting for these effects, GPS calculations could be off by miles. So every time you use your GPS to find your way, you're relying on Einstein's century-old theory. The theory of relativity also helps us understand the universe on a grand scale. It has led to the discovery of black holes, these mysterious regions of space-time exhibiting gravitational acceleration so strong that nothing can escape from it. It also predicts the existence of gravitational waves, ripples in the fabric of space-time, caused by some of the most violent and energetic processes in the universe. In fact, the detection of these waves in 2016 confirmed Einstein's prediction, opening a new window to observe the universe. Moreover, the theory of relativity impacts our ability to predict astronomical events. For example, it helps us predict and understand the bending of light from stars as it passes close to a massive object, an effect known as gravitational lensing. This effect has been used to confirm the existence of dark matter, a mysterious substance that makes up about 85% of the universe's mass. It's also important to note that the theory of relativity has led to the development of modern physics as we know it. It's one of the two pillars, along with quantum mechanics, that our current understanding of physics is built upon. It's been instrumental in the development of technologies like nuclear power, and has even influenced our philosophical understanding of reality. While the theory of relativity might seem far removed from our daily lives, it actually has a profound impact on technology and our understanding of the universe. In conclusion, the theory of relativity is a fundamental cornerstone of modern physics. It is a theory that has challenged our understanding of the universe, reshaped our perspectives, and continues to fuel our scientific advancements. Let's take a stroll back through the key points we've discussed. Firstly, we spoke about the special theory of relativity, which introduced us to the idea that space and time are intertwined into a single continuum known as space-time. We learned that the speed of light is the same for all observers, no matter their state of motion. This principle led to the famous equation EMC2, which tells us that energy and mass are interchangeable. Then, we ventured into the realm of general relativity. Here, Einstein took us a step further by revealing that massive objects cause a distortion in space-time, which is experienced as gravity. This means that the path a moving object follows is not straight as we might intuitively think, but rather, it's curved by the gravity of any massive objects nearby. From bending light to slowing down time, the theory of relativity has shown us that our universe operates in ways that are often far from our everyday experiences. It has been essential in developing technologies we rely on daily, like GPS systems, and in understanding cosmic phenomena, like black holes and the expansion of the universe. The impacts of the theory of relativity are profound and far-reaching. It has not only revolutionized the field of physics, but also has significant implications for philosophy, literature, and the way we perceive reality itself. In essence, The theory of relativity is an extraordinary testament to human curiosity and intellect. It's a reminder that our quest for knowledge is a journey, not a destination. And while we may not fully grasp everything about the universe, the theories we develop bring us closer to understanding the magnificent cosmos we live in. So next time you glance at your GPS or gaze at the stars, remember the incredible theory of relativity that makes it all possible.